Hi, everyone. Let's start. Okay, so the turn on video and yep. Today is the deadline for the take-home midterm. So first I would like you to ask questions if you have any. And after that, we continue chapter 6. Yeah. Do you have any questions? Fine. Okay, good. And after the midterm, I will discuss the final projects. So unless you have the sufficient skills in our coding, there is no point to discuss about the final projects. So after the midterm, I will discuss in detail about the past projects and the guideline for the project plan and also the project itself and criteria about how your presentation will be evaluated. Yeah, but overall, basically, as long as you finished the midterm successfully, I think the most students pass the course. I mean the vast majority. So but of course, the quality of presentation really depends on how much effort you spend. So some presentations are very good, and some presentations are they're okay. But yeah. Okay, so if you don't have questions, then we go to chapter 6, and the chapter 6. Oh yeah.
Quick
sure.
question.
Yeah, sure.
Now I'm having trouble with question 4, really kind of getting the code to compile. I'm getting a pretty consistent error message. I was trying to pull it up, but I'm getting a pretty consistent error message, something to the effect of the input isn't yielding. It's not yielding a numeric input. So I'm not doing something right now. Obviously, you can't necessarily help me with that. But my question is, should I still kind of put what I have for question 4 if I'm unable to get it to properly compile?
Yes. Even if you are unable to get the final results, then yeah, you can still get some partial credits still. So if you couldn't get the answer, still you can put it. Yeah.
Okay, thank you.
Yeah, and if your function does return the error, then I recommend you to run your code line by line, or even each object the output on your R console to see what's the error, the source of the error. But if you cannot really avoid it, then you can still submit the code. Yeah, sure.
Thank you.
Okay. And today's topic is actually not the linear regression, but the correlation. Correlation is a kind of the more fundamental concept to check the relationship between two variables, x and y. We don't have any order of the variables, just two variables, not predictor and response, but just two variables. And when we have the two variable x and y, the correlation, the Pearson's population correlation coefficient between two variables x and y quantifies the strength of linear relationship between x and y. For example, if you have the weight and the height of 100 people, then certainly I think a higher person is more likely to have more weight. It's not necessarily 100% true relationship, but as a tendency that we have, if we have height and weight, then usually we have some positive association between two variables. So if height is higher, then weight tends to be higher. And this correlation R quantifies how closely the W and H are related. For example, suppose the graph is like this. So always the higher height, it means higher weight, right? A larger weight. So that means the R is very high. But for this kind of relationship between H and W, still we have positive the association, but the relationship isn't really strong. So in such a case, the R is positive, but not very large. Sometimes the two variables have opposite relationship. For example, if we have 100 cars and we check the horsepower and MPG, usually the car with higher power have lower MPG. So we have negative association. So now Americans, they want to have, a car with higher power, with higher efficient MPG, but that is basically the contradicting hope. So we have the negative association, then we will get the negative correlation. So if you calculate the correlation between X and Y, actually the random variables between X and Y, we define this as this quantity, the covariance divided by variance of square root of variance of X times square root of variance Y, then we get this. We get, the quantity which can represent the strengths of relationship. And remember that the covariance is, okay, so at first the variance is defined by this one. So X minus expectation of X square, we take expectation of that. We also write the X minus mu X square, we take the expectation of this. So then we take square root. And covariance is a kind of extended version of variance. So we replace the one factor by another quantity, y minus EY. Then we get this. And this is a kind of similar to, okay, so this quantity doesn't have any unit. So suppose that, for example, X has the unit of maybe centimeter, and the Y has the unit of kilogram. Then X minus EX square that has the unit of centimeter square, then take square root. So that means centimeter. And kilogram, we have the same thing. So kilogram squared, then take square root, then kilogram. And on a numerator, X minus EX has the unit of centimeter, and Y minus EY, the unit of kilogram. So if we take expectation, still the unit keeps the same. So the unit for both numerator and denominator are centimeter times kilogram. So this is does not have any unit. It's like the proportion or something. Yeah. So that also implies that if we change the unit of X and the unit of Y, the still correlation coefficient keeps the same. For example, if we report the height by meter, then centimeter to meter, all numbers gets 100 times smaller. So if centimeter, 150 centimeter, that becomes 1.5, 170 becomes 1.7. So everything becomes the 100 times smaller, but still the R keeps the same. So R purely describes the relationship between X and Y and the invariant in units of X and Y. Yeah, and this one is described by the random variables X and Y, but what if we actually observe observations, the X1, Y1 to Xn, Yn? Then we define the R hat as S sub XY over S sub X times XY. So these are called the sample covariance and the sample standard deviations. So sample standard deviation of X is calculated by the square root of the sample variance. And sample variance is sum of Xi minus X bar squared divided by N minus 1. And also a slightly simplified formula is this one. So just we can avoid calculating X bar, and still that we can calculate the same quantity. So if we just simplify the first expression, then we can derive this one by just algebra. And Sy, the same thing for Y, and S sub xy is this quantity. So summation of the two factors, xi minus x bar times yi minus y bar, and divided by n minus 1. So this is called sample covariance. Yeah, and the sample correlation, we have n minus 1 on both denominator and the numerator. So if we cancel this, then we can simplify to get this quantity. So actually, we can avoid the using 1 over n minus 1. And S sub xy, okay, so here the n minus 1, the version which has n minus 1, but basically the numerator, it expresses this quantity. So we can avoid also calculating x bar and y bar. So I think that this is most informative graph in the section. So this represents the correlation. This describes the sample Pearson's correlation for several different data sets. So typical cases are on the top line. So if we don't have any relationship, correlation is 0. If we have positive association, then correlation is positive. Association is stronger, the correlation coefficient is larger, and association is perfect. That means the larger x. We have x-axis and y-axis. Larger x means always larger y, then correlation coefficient becomes 1. And one thing we have to be careful is that the correlation coefficient isn't the slope of the plot. Okay. So the slope doesn't really matter. So you can see this. This is a perfect relationship, that is all points are on the same straight line. Even if this slope is different, okay, suppose this is slope 1, but even if the slope is 2 or slope is 0.5, still the relationship can be perfect. So the correlation isn't the slope of the like regression line or trend line, but just the correlation describes the strengths of the relationship between the two. And the negative side, the same. So larger x means the smaller y, that is negative correlation. And if correlation is stronger, the relationship is stronger, then correlation gets closer to 1. Negative 1. So even if the slopes are different, still the correlation can be the same, the 1 or a negative 1. Also, the correlation of 0.8, the slope doesn't really matter. The strength is the same, then we have the correlation coefficient 0.8. And the center one, why this does not have any number? They have any idea? So remember the definition of correlation coefficient. So definition is the S sub x sub y over S sub x times S sub y, right? And what's the problem here? In this case, we don't have any variability in y. The y value is almost the same, always the same, y bar. So we cannot really calculate this S sub x. So denominator becomes 0. So we cannot define this. So that's why that we don't have any number here. So we cannot define the correlation. So in statistics, many concepts cannot be considered if we don't have any variability. So in statistics, assumption is that our data have some variability, then we see if that variability is significant. So if we don't have any variability, then usually we cannot calculate something. And that's why we don't really have correlation. And the bottom lines, bottom panes, so these are all relationship between x and y with correlation 0. So certainly x and y are related. X and Y are related, but we don't really have the linear tendency. So larger X does not mean, larger X neither mean larger Y or smaller Y. So you can see that this has clear pattern, strong clear pattern, but we cannot say when X is larger, Y is larger, or X is larger, then Y is smaller. We cannot really say that. But we have a very complicated relationship between X and Y. The same thing by this one and this one. So we certainly have a relationship. If we have X value, we can specifically mention what's the value of Y, the range of Y. So certainly it's related, but still we don't have any tendency. So if we consider, for example, the trend line, the linear trend line, actually any line is indistinguishable. So any line cannot be the trend. So this line is as good as this line or this line or this line. So we don't really have any trend line. So that's why correlation coefficient becomes 0. So we don't have any relationship such as X is larger than Y is larger or smaller. The same thing for this one or this one and this one or this one, this one. So last one, we have clusters. So still we have a relationship between X and Y, but no linear relationship. So no correlation between X and Y. So correlation coefficient can describe only linear relationship between X and Y. And we cannot quantify the nonlinear relationship. So imagine that suppose we have 100 observations, then 100 observations have the very complicated pattern. And if correlation coefficient is just one number, then sometimes it's hard to quantify very complicated relationship. So you can imagine. Actually, if you have more complicated quantity, actually we can detect if these cases have some relationship between X and Y. I got two. Oh yeah, so division is by 0. So yeah. And I have one question. I got one question. Have you ever seen a square or ring-shaped scatter plot within real world data? Certainly it's possible. This one may be the pretty artificial, but for example this one. So in many countries, for example, the train stations or even the road are circular shaped. And if you see, for example, population distribution, so those populations are concentrated on a circle or something. So that's certainly possible. So yeah, so I feel this and this are pretty artificial. This is a kind of the distorted, the uniform distribution. So yeah, I think still it's possible, maybe. Maybe yeah, I don't I don't really know, but yeah. So I think linearly transformed uniform distribution. So mathematically it's possible. And another comment, my friend wants to know if you'd see the double parabola shape. Okay, this one. Yeah, that's also pretty artificial. And yeah, I haven't really seen any yeah, I think I don't come up with this pattern. Yeah, that's right. So clusters are certainly possible, right? So for example, the 4 species of animals, then if we put those data in the same pane, then certainly we have 4 clusters. So that's pretty natural. And this is a kind of natural still. This is, yeah, I don't know how common it is. These are maybe mathematically natural, but this is pretty artificial. That's true. Yeah. Yeah. So people say these are, toy examples. Many mathematical books have toy examples. Okay. And the more kind of mathematical properties. So you can see that the R is always between -1 and +1. And That can be proved by the Cauchy-Schwarz inequality. Cauchy, maybe CHY. Cauchy-Schwarz. Yeah, maybe the basis to show the maybe triangular inequality. So Cauchy-Schwarz inequality. And so mathematically it can be proved. And if R is equal to 1, then xi and yi have perfect positive linear relationship. That is, all xi, yi's are on a straight line with a positive slope. So slope doesn't really, so R is equal to 1 does not mean a specific slope, but at least the positive slope. And yeah, so for example, this. And if R is positive and xi and yi have positive linear relationship, so if we fit y on x, then y is equal to a plus bx, then this b should be positive. Yeah, so we cannot specify b hat itself, but at least we know that this is positive. If R is equal to 0, there is no linear relationship. Actually, this is the definition of the linear relationship. If R is 0, then no linear relationship. There may be some nonlinear relationship as seen in the previous figure. And R is positive, basically the similar thing applies. xi, yi have negative linear relationship, so b hat is negative. R is equal to -1, we have perfect negative relationship. That is, all points are on a straight line with a negative slope, like this. Okay, so now that we consider why this R can quantify the positive or negative linear relationship. And okay, so at first, the denominator is always positive. So the sign is determined by the numerator. And the numerator is basically the summation of this term over all i's. So basically the sign of this quantity, xi minus x bar times yi minus y bar. So this matters for the sign of R. And these figures explain the sign of this quantity. And the first case, okay, so we have the x-axis, y-axis here, and x bar and y bar. So we basically divide the entire plane into 4 quadrants and see if what's the sign of this quantity. Then you can see in the upper right quadrant, you can see that the xi is always larger than x bar. You can see xi is this value and x bar is this value. So this first factor is always positive. So these areas, the first factor is positive. So this is positive, okay. And also in the so also if the yi is larger than y bar, the second quantity is positive. So in this range, the second quantity is positive. So this first factor is positive, and this range, the second factor is positive. So that means that in the quadrant 1, both first factor and the second factor are positive. So we can see that the product is positive. And also in the third quadrant, the first factor is negative, second factor is negative. So product is positive. And in the second and the fourth quadrant, we have negative, negative. So that means that if we have positive relationship between x and y, more observations are in this quadrant and this quadrant, right? So that means that we have positive linear relationship. Okay, so it's not really exact proof, but we can see that as a tendency. if we have positive linear relationship, then for most observations, this quantity is positive. So that means the summation of this quantity becomes positive with very high probability. So that's the reason that this quantity, sum of this quantity, is related to positive linear relationship. And the same thing for the negative relationship. If the x and y have negative relationship, then most observations are in the quadrant 2 or 4. So mostly the product is negative. Or if we don't have any linear relationship, basically observations are well distributed in these 4 regions. So that makes almost the summation nearly equal to 0. So that's the reason for why the correlation coefficient quantifies linear relationship. And this is a computational statistics class. So we don't really have to calculate the correlation coefficient by hand, but this is one example. So, okay, so suppose that we have x-axis and the y-axis and x and y, then we have 5 observations. X is 1 and y is 20. Y ranges from maybe 0 to 20. X ranges from 1, 3, so about 10. So maybe this is around 5, this is around 10. And the 120 is around here. And the 38 is around here. Maybe a little around maybe here. And 610 is around here. And the 80 is around here. And the 212 is around here. So you can see probably these 5 observations have a negative correlation. And actually, if we calculate the covariance and variance, that we can calculate the variance of x first. Variance of x is 8.5. Variance of y is 52. Covariance of xy is negative 18. So if you calculate the sample correlation coefficient, this becomes negative 0.856. Any questions? Yeah, so here is an exercise. So you can run this exercise, recalculate the correlation coefficient R hat above with R in 2 ways by using correlation function. The correlation function calculates this directly, so it's quick. But also you can just go back to the definition. So definition is here. So you can use this definition to calculate the covariance. Sorry, the correlation coefficient. Sorry. Yeah. So now, okay, we are doing statistics. So that we want to do estimation on R hat and also the testing on R hat. So sometimes, okay, so maybe your friend is a medical doctor, and he or she asked you about the conclusion. So so they have some data of 2 variables. Okay, so they have the weight and blood pressure, if those 2 variables are related or not. And they found that correlation coefficient is 0.3 or something. But want to see if that correlation is really significantly different from 0. And then we have to do some testing. And here is the theorem. So we can test this null hypothesis, R is equal to R naught. Often this hypothesis is R is equal to 0. Against alternative, so R is not equal to 0. And we can use this test statistic to prove it. So usually they're based on our data, we calculate the test statistic. So this is test statistic. So in t-test, we have to calculate t-statistic. And here we have to calculate this quantity, 1/2 times log of 1 plus r hat over 1 minus r hat. So once you know r hat, it's very easy to calculate in a computer. And basically, this transformed version of r hat approximately follows this normal distribution. So this is based on the central limit theorem. So of course, if sample size is small, it does not apply. But the reasonably large sample size, n, that we can approximate this left-hand side by normal distribution with this mean and this variance. So of course, if n is larger, the r hat is more accurate. So this quantity also has smaller variance. So large n, the variance goes to 0. And this quantity is, okay, so the denominator is between what? Sorry. So denominator is between 0 to 2, right? And the numerator is 1 minus r naught. So I think this can be any, oh yeah, so this can be any number between, so 2 and -1 and +1, so 0. So actually the ratio can be any number, And using this, that we can test. So to be, yeah, I think I didn't mention it specifically, but yeah, so suppose this is test statistic. We can say this as maybe z, since this follows the normal distribution. So basically, we can see the z minus 1/2 times the, sorry about that. Z minus the 1/2 times, 1/2 times the log of 1 plus r naught. Often r naught is 0, so over 1 minus r naught. So divided by the square root of, square root of 1 minus n minus 3. So this follows normal 0, 1. So using the normal distribution, the quantile points, then you can see how this is, you can see, so how extreme this observation is. So if so basically if this quantity, so maybe we say this as z tilde, and the reject h naught if the z tilde is larger than the z sub 1 minus alpha over 2. So in this way that we can test if, we can test if the z tilde is, yeah, so z tilde is significantly, so we can test if h naught. So r is significantly different from r naught. You can decide. Yeah. And I got one question. So if n is large, then since the variance is small, wouldn't the distribution be almost degenerate? Yes. The central limit theorem, always the idea is like that. So basically, n is large, then this converges to degenerate distribution, right? So 1/2 times log of 1 plus r naught over 1 minus r naught, and the distribution looks like this, right? If n is large. But if we standardize it, so z minus mean over the variance of this, then actually this quantity will be larger. So basically the situation is we magnify this range. Okay? We magnify this range so that we can still see the normal shape. So that is usual phenomenon. Okay, so the central limit theorem. Why we say central? Because we describe the behavior of random variable around the center. So if you magnify the center, we rescale this graph and we magnify this, then still it looks like normal. So that is the reason for central limit theorem. Yeah, that's a good question. It's probability question. So, okay, so we have seen the condominium example. So we have the relationship, the square footage and price of condominium. So yeah, we can see, I think this is in page earlier one, so this one. And you can see that even you don't see the trend line, at least we have positive relationship between two variables. So we expect that this is significantly different from zero. The correlation is significantly different from zero. So we want to see that by this test. So where is that? Yeah, so correlation is 0.674. And if we do the test based on this Fisher transformation, then yeah, actually they call this as the T statistic, and this is approximately Z, but the R uses the slightly different approximation. So we use the T distribution with degrees of freedom, the 46. This is almost the same as normal, right? Normal 0, 1. So T distribution, if DF is, I say, larger than 30, then almost normal. Then based on this test, then it follows actually, so that we can get the p-value of the less than 10 to the power -6. So we can say that the correlation coefficient is significantly different from 0. Yeah, I think that we have some option to change the alternative hypothesis, null hypothesis. So here, the null hypothesis is R is equal to 0, but we can change this into other numbers. Maybe I can check it for now. Yeah. I cannot really see the option here. So maybe you have to go back to the theorem to test if R is not equal to 0. Yeah, I don't know. When I see the help of the correlation test, COR.test, we don't have any option to set the null hypothesis. So always they test R is equal to 0. But if we use the theorem, then we can just expand this. Okay, so any questions so far? Yeah, so the theorem, here theorem is probably the not most informative version. So the R claims that this quantity is approximately I think the T distribution with this quantity. So this quantity is rather T distribution with degrees of freedom n-2. But anyway, n is larger, then this is normal. And if n is smaller, anyway, so this approximation is not good. So I think it's not a big difference, but you can use either T distribution or a normal distribution. Yeah, so some exercise that if you have data, maybe the iris data, sepal length and the sepal width, that we have seen that these two variables have positive association for first 50 observations of iris dataset. So we can check if we can test if R is equal to 0. And also we can try manually from the theorem. Yeah. So that's for the correlation, the Pearson's correlation. And now we want to see the relationship between the R hat and the regression line. So at least we know that the R hat is positive, that is equivalent to B hat is positive. So, you know, R hat is not equal to B hat, but at least we have some relationship. So R hat is negative, then B hat is negative. And R hat is 0, then of course the B hat B hat is equal to 0. So at least we have some relationship. So what's the exact relationship between R hat and B hat? Then actual relationship is here. So B hat is equal to R hat times S sub y over S sub x. So we can say that the B hat is, maybe I would say that the R hat is the rescaled version of B hat. Because basically, you know, S sub x is the scale of x, right? So if x is reported in meter, so suppose that S is equal to 0.1. If X is reported in centimeter, then the standard deviation should be 100 times larger, so 10. So basically S is the scale of, standard deviation is scale of this variable X. Right? So if we change the scale of R hat, sorry, we change the scale of R hat by the unit of X and the unit of Y, then that becomes B hat. So that is the relationship. You know, if all Y values are 100 times larger, of course, the slope should be 100 times larger. So B hat should be 100 times larger. But the R hat just purely express the relationship between x, y, and the strengths of the relationship between x and y. So R hat should not change, but the B hat should be 100 times larger. So it's pretty natural that the B hat is R hat times S sub y over S sub x. I have got another question. The R hat could also be undefined if B hat is 0 and vice versa. Also be, oh, sorry, that's true. That's true. So maybe the 0 isn't really, this isn't really accurate. Yes. So the B hat is equal to 0, then it's possible that the R hat is 0. Or R is undefined. Yes, you're right. So as long as R is defined, this is equivalent. But yes, yeah, you're right. So yes. And R hat could be also undefined if B hat is 0. And the B hat is also sometimes undefined. That's true. So if the Y doesn't have any variability, then B hat is undefined. So maybe or undefined. Yes. Yeah, and another way to put it is the B hat and R hat are equal if the standard deviation of X and the standard deviation of Y is equal to 1. Yes, and B hat is R hat multiplied by the scale of Y and divided by the scale of X. Yeah, actually in computer science, often all variables are standardized because different scale have just bring the problems, right? So if the scale of X is very small and the all X values are less than 10 to the power negative 8, then we have numerical problems. So it's more reasonable to assume everything have standard deviation 1. So in that world, that we can say that the B hat and R hat are the same. So that is another reason that the people are confused between R hat and B hat. Some people think that those are exactly the same. But without this assumption, standardized assumption, the R hat and B hat are different. Yes, and example 3, sorry, another example. So here that we compared R hat and B hat. So this is the linear regression. So we get the B hat is equal to 0.2473. And correlation coefficient, that was 0.6 something. So it's different. But if we multiply the standard deviation of price, this is Y, and the standard deviation divided by standard deviation of X square foot, then we get exactly the same number. So this is R hat times S sub Y over S sub X. Yeah, so I think that that is the correlation, Pearson correlation coefficient. And we will discuss another type of correlation coefficient. So that is the Spearman's correlation coefficient. And before that, we want to define the order statistics. So when we have several observations, just that we order these observations, and those ordered observations are denoted as the X sub parenthesis 1 to X sub parenthesis 4. So these are called order statistics. So the third one, X, the parenthesis 3, is called the third order statistic of X. And here is the Spearman's rule. Before the correlation coefficient, I think I have to make one note, and I think the updated version of slides include that. But Pearson's correlation coefficient. Yeah, so our notation in the textbook and my slides is the population version. We have R, the Pearson's correlation, R, and the sample version, R hat. But often the notation is the population correlation that we have, what? Yeah, I think often the population correlation rho and the sample version R. So this is another notation. But we don't use this rho because we reserve this number, this letter for the Spearman's correlation. And here the example, the definition of Spearman's correlation. So Spearman's rho is the Pearson's correlation coefficient for order statistics, which are invariant by monotone transformation. So maybe this, sorry, so I think that this is not really accurate description. So Pearson's rho is, so the Spearman's rho is Pearson's correlation coefficient for the rank statistic, the rank of observations. So which are invariant by monotone transformation of data. And since this is another version of Pearson's correlation, the rho is similar to R, and that is between -1 and +1. And sample version, also the same thing. So maybe it's good to see the examples. So suppose that we have the same 5 observations, and we ignore the size of these observations, but we just focus on ranks of these observations. So if we have the 5x values, we have rank. 1 is smallest, and 2 is second smallest, 3 is third smallest, 6 is fourth smallest, and 8 is fifth smallest. So we use this R sub xi to calculate correlation. And also for y, the 0 is smallest, first smallest, and 8 is second smallest, 10 is third smallest, and 12 is fourth smallest, and 20 is fifth smallest. So we calculate correlation between these two variables. Then, yeah, to be exact, we calculate the squared observation of Rxi and Ryi, and the product of these two. Then we can calculate the Pearson's correlation between R sub xi and R sub yi. And that becomes negative 0.9. So this is called the Spearman's correlation. And the Spearman's correlation has some advantage if we have outliers. So for example, imagine the situation that these numbers have outliers. For example, this 20 becomes 200. So this one becomes maybe negative 50 or something. So then the Pearson's correlation always approaches to -1 or +1, because one extreme observations almost determines everything. Other 4 observations do not have any linear relationship between x and y. Still, if one observation is extreme, the overall that we have very strong correlation. So this becomes probably the correlation coefficient of nearly -1, right? But this is just based on the fact that there is one outlier. So the Pearson's autocorrelation, the Pearson's correlation coefficient, Spearman's correlation coefficient, makes the impact of outliers smaller. So just that we have 5 observations and we give the 1 to 5. So it's more robust against outliers. So that is the one benefit of using Spearman's correlation. Of course, the numeric information is lost when we calculate ranks. So I think that it's harder to reject, for example, null hypothesis that the correlation is 0. But still, this is much more robust statistic compared to Pearson. So that's why the people often use this Spearman's correlation. Yeah, and the Spearman's correlation can be calculated by the same function, the COR, but just specifying the method is equal to Spearman. And the good thing for Spearman's correlation is that it's invariant when we transform x or y by monotone transformation. So square of x. So think about the z's equal to square root of x. So this is monotone function. So we can see if x is here and z is here. So this is monotone transformation. Larger x always means larger z. So the same thing for this transformation, y to the power 0.4. And the Pearson's correlation changes. Originally, I think correlation is negative 0.857, but this becomes negative 0.826. It's not too bad, but it's not constant. But the Spearman's correlation, the negative 0.9 just keeps the same. So it does not change by monotone transformation. So it means the more objective than the Pearson's correlation. Right? Yeah. Another formula for, yeah, so Spearman's law can be calculated by different way. So this is the equivalent expression for Spearman's law. So it's slightly simplified in the sense that we don't have to calculate the average of rank of xi and average of rank of yi. But the average of xi is clear because if we have 5 observations, then average is 3. So immediately we can tell. So I don't know how much benefit this expression has, but just we have another expression. Rho is equal to S over N to the cube minus N. Yes, so actually these are just the sample version of Spearman's correlation, and that we don't really define the, yeah, we can define, but we haven't defined the population version of Spearman's rule. So that means the Pearson's correlation and the Spearman's correlation. The population version, we define this as R, and the sample version we calculate as R hat, and here only rho. So actually this is missing in this textbook. But anyway. Yeah, so that's the case. And also Spearman's correlation, we want to test if the rho is equal to rho naught. And this has a little more accurate test than Pearson's autocorrelation because the distribution of R of, the rank of xi and the distribution of rank of yi is given. Right? Because if we have 5 observations, the distribution of this is, we know, the 1 to 5, and this is 1 to 5 as well. So assuming we don't have any ties, that we know the distribution of this. So we can calculate, we can test this hypothesis more accurately. So in Pearson's case, it really depends on the underlying distribution of x and y, but the Spearman's case, we get more accurate distribution if we simulate the distribution of rho hat. So that means that we just randomly assign this and this based on the assumption that x and y don't have any relationship. Then that we can test this. Actually, that is probably hard for rho naught is equal to, that is simple if rho naught is equal to 0. If not, the simulation is much more complicated, but some people have done that. So it's not a problem to use the Fisher's transformation, but the point is Spearman's rule that we have slightly more accurate version of the test. And yes, actually that we can do this in also using the same test, the COR.test. And the surprising, this is X and Y, so we only have 5 observations. And the only 5 observations, it's pretty hard to reject the null hypothesis, but this is p-value for that. Yeah, it sounds that this test is constructed on this S. S is the quantity defined here. So S is small, that means xi and yi almost has the same rank within x and y, respectively. So that means we have higher correlation between x and y. So using this S, that we can test if the correlation is 0. Yeah, so that's it for today. And actually, I have another one, the Kendall's tau. But yeah, this is a kind of similar idea to Spearman. It's even simplified version. So, not really. Sorry. We can combine the idea, but yeah, it's not, sorry. It's not really the simplified version of Spearman, but the simplified version, some kind of simplified version of Pearson. So we only care about the sign of this factor. So basically, this factor plays important role to determine the sign of Pearson's correlation coefficient. But basically, we count the number of positive products and the number of negative products and take difference to define a correlation. But I think usually the Spearman and the Pearson are sufficient to analyze data. So I would like to skip this section. I got one question. So Kendall Jenner. Oh, sorry. Sorry, I'm not knowledgeable enough about the full name of Kendall. Yeah. Sorry, I don't really know. So who's one? His name is Maurice. So Maurice Kendall. Okay. Yeah, so that's it for today. And I think that today is the deadline for the midterm. So I would like to finish a little early. Probably that's fine. So if it's in the midterm is in class, then actually no lecture for one day. So yeah. And do you have any questions?